Welcome to this video lesson on echoes and calculations involving echoes. So, what is an echo? Well, I think most of us have experienced echoes when we are in a very big room and it's empty and it's got hard floors and there aren't any curtains. And when we speak, we hear echoes. There are these reflections of our own voice, the sound that we make. It could be our footsteps that we know we're making the sound, and then a few seconds later we hear it come back to us. And if we make continual noise, continual sounds, we're going to get reverberations as these reflections come back to us. So an echo, in essence, is the reflection of sound waves. So let's just define this. Echo is the reflection of sound waves. Now, let's look at an example. You might or you might not have experienced this if you go hiking and you are walking up a ravine and there are these rock faces on either side of you, and as you shout, you will hear, a few seconds later, you will hear the sound you made come back to you. So let's assume that you're doing this, and you are the source of the sound. And you make a sound, let's say you shout out your friend's name, then the sound waves are going to move out toward the rock face three-dimensionally. But in the direction of the rock face, they're going to move toward the rock face. With the rock face being hard, it's not going to absorb a lot of the sound, and that's very important for echoes. Echoes are invariably created in environments where there aren't things like carpets and curtains, which are soft substances which absorb the sound and therefore don't reflect the sound. So we've got a hard rock face here, and the sound is made by the source. The sound now travels toward the rock face at the speed of sound, and let's assume that speed of sound is 340 meters per second in air. It does vary based on density of air and based on the temperature of the air, but let's work with an average of 340 meters per second. So it's going to take some time for the sound waves to reach the rock face. So let's assume that the distance to the rock face is d. So d is distance, and the distance is going to be in meters. We're going to work in meters, distance in meters, because the speed of sound is in meters per second. Then what happens is it's going to take a certain amount of time. Now, that time, let's call that time interval delta t. That's the time interval, and that's going to be in seconds. Then using the formula that you should have learned in early high school, that speed is distance over time, velocity is distance over time, delta t. We are now able to work out what the distance is if we have the time, or what the time is if we have the distance. So let's assume that when the sound hits the rock face, that it's hard enough for most of it not to be absorbed, but to be reflected back. There will not be a change in wavelength, there will not be a change in velocity, there will not be a change in frequency. So what's going to happen is that the sound is going to be emitted. It's going to travel toward the rock face, and then it's going to travel at the same velocity back toward the source. So let's assume the time let's assume in this case that the time is 5 seconds. Let's say time is 5 seconds. All right, and to make things simpler, I'm just going to say this is t total. This is the difference in time between when the person makes the sound and when the person hears the sound. So in that 5 seconds, the sound is going to move toward the rock face, be reflected, and come back. So the velocity we're dealing with is the velocity of sound. Now let's assume that we want to know how far away is the person from the rock face. So we want to know how far away. How far away? Well, if we rearrange and we say distance is velocity times the total time, then we're going to get the total distance that the sound waves have traveled. So we've got distance equals Vs, which is 330 meters per second. T total is 5 seconds. So the distance that the sound has traveled is going to be 1,650 meters. Just going to check that with my calculator. 300 times 5 is 1,500, and 30 times 5 is 150, so it should be 1650. Just going to check, not assume, that's correct. So that's 1,650 meters. Now, that was easy enough. It's wrong. Why is it wrong? Well, we were asked not what the total distance is that the sound traveled, but how far was the source from the rock face. So we need to be careful here. If we want to work out what the distance is in meters between where the source is and where the wall is, we must work not with the total time, but we must work with half of the total time. You see, it's going to take, if the total time to go for the sound to travel from the source to the wall or rock face and back, then because the speed of sound doesn't change in the air over that period of time, it's going to take 2.5 seconds for the sound to go from the source to the wall, rock face, and then another 2.5 seconds to go from the rock face back to the source. So we in actual fact need to divide by 2. So therefore, the d, which is the distance between the source and the rock face, that is going to be 330 meters per second. T total is 5 seconds, but we've got to divide by 2. So therefore, the distance is going to be 330 divided times by 5 seconds divided by 2, or 330 times by 2.5, and that is going to give us 825 meters. And that is the correct answer. So now, this is the trick with echoes, is that when you're working with the time, very often we give you the time between when the sound was made and when the sound is heard. But that time is not the time that we use for the distance between the source and the reflecting surface, but rather that time needs to be divided, that total time needs to be divided by 2 before using it in the d equals v times t formula. So let's now move on to an exam type question. So in this question it reads, while Mr. Himon is hiking on Table Mountain, he gets to a ravine with 2 very high rock cliffs on either side of him. Being the scientist Mr. Himon is, he claps his hands and waits for the echoes to come back to him. He records the time with his cell phone's stopwatch. The speed of sound on the day is 340 meters per second. The first echo comes back after 1.1 seconds and the second echo 0.4 seconds later. How wide is the ravine? So Mr. Himan claps his hands, the sound being a longitudinal wave in 3 dimensions. The sound is going to move out at 340 meters per second. Notice, according to the drawing, the sound is going to have to travel further before it hits the left-hand rock face and gets reflected than on the right-hand side. So this sound wave is going to echo sooner, let's call that 1, than this one, which is going to echo later. So we want to know how wide is the ravine. So I'm going to call this distance here. I'm going to call this distance, I'm going to call x1, or let's call it distance 1. Let's call that distance 1. And on the left, we're going to say that this distance is distance 2. Right, so we're going to need to find each of the distances separately, and then adding them together will give us the width of the ravine. Right, so now we know that the velocity of sound is 340 meters per second. It's been given to us. We are told that the first echo comes back after 1.1 seconds. So the time it takes to go from Mr. Himan to where I seem to have lost my arrow, to the rock face on the right-hand side, that time and then back is 1.1 seconds. So the time from Mr. Himan to the rock face is half of 1.1 seconds. So therefore, we're going to say that T1 is going to be 1.1 second divided by 2, which is going to be 0.55 seconds. And distance, D1, is Vs, the velocity of sound, times T1. It comes from velocity is distance over time. So distance 1 is going to be 340 meters per second. Time 1 is going to be 0.55 seconds. So D1 is going to be 340 times 0.55. That is going to be 187 meters. Now we do exactly the same thing for D2 on the left. So we're going to do that. So the velocity of sound is exactly the same. Now, what one needs to be careful of is how you interpret the question. So it says here that the first echo comes back after 1.1 seconds, and the second echo 0.4 seconds later. So it's not that it takes 0.4 seconds for the echo to return. Let's just bring down the diagram. It's not that it takes 0.4 seconds for the sound to go out on the left-hand side and return, because that wouldn't make sense, because it's going to take longer. It says 4 seconds later. So after the first echo returns, the second echo returns 0.4 seconds later. So what that means is T2 is 1.1 second plus 0.4 seconds, which is 1.5 seconds. And we need to divide that by 2. And so that is the tricky part. So that's 0.75 seconds. Now, distance 2, which is the distance between Mr. Himan, there's Mr. Himan, and the wall, that's going to be the velocity of sound, Vs, times T2. So this is going to be 340 meters per second. T2 is 0.75 seconds. And so therefore distance 2 is going to be 340 times 0.75. And that's going to give us 255 meters. Right, so we now have, going back to our diagram, we can see that D1, that's 187 meters. D2 is 255 meters. Right, so the width is going to be D1 plus D2. So D1 is 187 meters, D2 is 255 meters. So the width is going to be plus 187, that is going to be 442 meters. So this is the standard type of echo question that you would get in your exams, where you're actually dealing with multiple echoes, and from those multiple echoes then you're asked to work out, for instance, the distance between the two rock faces. There are various variations of this. It all depends upon, obviously, the physical context, but the basic method is what I've shown you here, is that you work out the distance or the time, depending on the question, separately for each of the echoes, and then once you've done that, you can then put the answers together for that quantity which they're asking you for. It could be the width, it could be the total time. It all depends upon the question. So I hope that this video lesson has helped you to be able to deal with and approach echo type questions in the grade 10 physical science syllabus.